So here's the Pioneer SX-990, and she is dirty. So that's not bad at all. Be fun to work on. But the first thing we're going to need to do is clean her up. Apparently, she doesn't have any sound out of the right channel. The FM signal tuner works, and it seems to be calibrated correctly. That's good. But man, dirty. Even look at this. I went flying. So
the SX-990 was released in 1970 and had a price tag of $299. It was a middle-of-the-road receiver and put out 28 watts per channel into an 8-ohm load. The front design is clean and has a pleasant appearance. One slight downside to this model are the presence of speaker plugs instead of terminals. The 990 has pre-outs, main ends, and a center channel output. It is considered by some to be one of the best sounding receivers with a warm, tube-like sound.
Well, we'll get this cover popped off and take a look at it. Well, I got the case off, and the good news, I found $1. The future is looking good. Other than that, it's dirty on the inside, just like it is on the outside, but it looks to be unmolested from a technical standpoint. Everything looks to be original so far, but we're just now getting into it, so we'll find out. The lamps look fairly easy to access, but famous last words. We'll see exactly how easy those are to access when you get in there. Now, that doesn't exactly look factory to me. Looks like someone has marked that capacitor right there, so I'm probably not the first person who has been in here. It's definitely been a while since anyone has been in here. Unless they came in dropping dust with them. Okay, after cleaning up the top side of the case with a vacuum cleaner, I've removed the bottom side of the case and the power supply shield. And it looks like most of this is original. Well, I found a problem on the power amp board where you see the yellow jumpers. There are 2 fuse holders there, and one of the fuses is this fuse here, and it was as blown as could be. So what I did was I just put some jumpers on those 2 fuses to check and see if we have a dead short.
Okay, let's pump the brakes for just a second. Most people would probably recommend replacing the blown fuse with a new fuse. I have this receiver plugged into my dim bulb tester, which limits the amount of current the amplifier can pull to a very small amount. That is why I feel comfortable simply using jumpers in this situation. That said, now is probably a good time for my public service announcement. Electronics can be deadly. My videos are for entertainment purposes only. If you attempt anything you see in my videos, you are doing so at your own risk.
As you can see, one of them is not plugged in. This is the right channel, which the previous owner said that was the problem. There was a problem with the right channel, so I'm suspecting a blown output transistor. But let's hook this back up, and then we'll check the dim bulb to see if we have a dead short. Okay, so what I'm going to do now is I'm going to turn the power switch on, and this is probably going to light up very bright. And if it does and it stays bright, I'm just going to turn the receiver right back off. And there we have it, dead short. Now we know it's a dead short on the right channel because I just unhooked one of the jumpers, and I'm going to turn it back on now. And that's what it should look like instead of having a dead short. Okay, so the next step is going to be to pull the amplifier board completely out and test all the output transistors there and find out which ones we need to replace. Most likely are going to have to replace all 4. So let's get busy with that. All right, we have one other disturbing discovery, and that is some output DC on the left channel here. This looks like we have more than half a volt of DC on the left speaker A output. So that's not good either. All right, well, I finally got the board out. And can you tell which way was up? I think you can. A little bit of dirt on this baby. So next I'm going to get these heat sinks off and transistors out and start testing. I'm confused. Well, crap on a cracker. Okay.
Well, I lost the footage, but cleaning went on for quite a while. Here, the board is cleaned up and ready to examine for any obvious signs of damage or wear and tear. This is the damaged emitter resistor R33 for the output transistor Q11 that is highlighted in yellow on the far right side of the board layout. Here are the 2 output filter capacitors. These are C13 and 14 and are supposed to be 1000 microfarads at 35 volts. Both are reading very high. I wanted to make sure I knew where each of these potentiometers were set before I started messing with this board so I could put them back in roughly the same spot if I accidentally moved one or needed to replace any of them. As you can see on the right, VR3, which is supposed to be a 50K pot, is not looking good and needed to be replaced. This is just a shot of the cleaned up board with the emitter resistors and output filter capacitors removed. In this photo, I'm just marking spots with a paint pen that need attention.
Okay, so I've added 2 gallons of distilled water already. And now for each gallon of distilled water, you put in 3.2 ounces of this ultrasonic cleaning solution because it's a 40-to-1 ratio. So I have a cup here. I'm going to measure out 6.4 ounces roughly, and we'll go with 6.5-ish. That's good enough. It's good enough. All right. And we're going to degas this liquid. And then we'll come back. Okay, so now that's done. We're just going to wait and let it heat up, and then we're going to put our stuff in. While the ultrasonic cleaner is heating up, you can see that it pulls about 561 watts or so. Okay, we're all heated up to 50 degrees Celsius, which is 122 degrees Fahrenheit. So now we're going to put our items in and start it. It's a bit warm. All right, let's get that started. And now we wait. And there we have it. That water is dirty. Very dirty. You can see all of that. I don't know if you can. There's all kinds of particulates at the bottom. Okay, let's see how it did. Just pop these open. These look fairly clean. I would say they look very clean. They look new. The fuse even looks perfectly clean. The screws look clean. The grounding screw looks clean. Everything's good to go there. This was another shielding that goes over the power amplifier. I think I should probably wash these off, but I'll do that in a minute. But this was very dirty, and now it is very clean. It's beautiful. Looks really nice. What else do we have here? Okay, what do we have? What's in here? I don't want to mix these up. We have some screws. Still some tarnishing from these, looks like copper screws. So I'll have to clean those individually. That didn't do much good on the copper screws, but everything else looks great. Put those back in there. Those go in a specific place. I have a wife's wedding rings. She'll be thrilled to know that I cleaned them in the same liquid as all of the other stuff. Looks pretty good. I think it looks pretty good. She's going to be happy about that. Let's put those over there. And of course, we've got knobs. Let's see how these came out. And those look good. Those look really good. Those are super dirty earlier, and they are super clean now. That's very nice. Everything in there looks really good. So we'll just put those back in there. We're going to wash them all off, so I'm just going to leave them in the basket for now. And then we had the AM antenna bracket, and that was very dirty, and now it is very clean. Beautiful. Yeah, happy with that. And then the main power amp board. I cleaned it really good earlier, but it looks even better now. I mean, it looks really nice. Okay, so what we're looking at here is the remnants of board W15-060. And what I'm about to replace are the 4 emitter resistors, which are R33, R31, R32, and R34. And those are here, 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 and here. The spec calls for 2-watt half-ohm resistors, so I'm going to replace them with 3-watt equivalents. Now, I don't know that this machine will ever be worked on again, or receiver will ever be worked on again, but to be friendly to your next technician, make sure that they can read the component values, so bend the leads so that you can read them from the top. There. Easily readable from the top. Soldering on camera with the camera in the middle of the screen is a lot harder than it actually looks. God, that is ugly. Can I do this and not hit the camera? Much better. All right, camera. You are in the way. I'm going to have to come back to that because there's another component that goes in that slot. Okay, this is just isopropyl alcohol. And we're just going to clean up all that flux. Okay, so the emitter resistors are in. I think the next thing I'm going to try to attempt to tackle on this board is this potentiometer here. Probably going to put the new capacitor, the large 1000 microfarad capacitors on this side and the other side last because they take up so much space and they're large, and the new capacitors are actually two lead capacitors instead of 4. If we look at the old capacitors, we can see that they had 4 terminals and only really 2 of them were used. Clearly the other 2 were tied together and that's set directly down on the board and clamped to the board. The new capacitor, however, is just simply a 2-terminal capacitor, so we're going to have to do something a little different on here. So that's going to save that problem for later. Now the potentiometer is too large, so what I'm going to end up doing is probably just cutting most of this off because it will actually sit on the board here like that, and it will kind of just be in the way. So I'll probably cut it off right where the ridges start, so you'll end up with just having this portion left over. I think that's sufficient, seeing how it's just it's not going to be adjusted all the time, so that's good enough. So let's start with that. Ooh, a blade is already on it. How convenient. Okay. That'll work. That'll work fine. Now let's just put a little slot in the top. There. That's a little bit janky, but yeah, it'll work. And I think a screwdriver will fit in there just fine. Yeah. Good to go. I'll clean that up a little bit on the edges there. But that looks good. That won't take up much space. Okay, if we take a look at the PCB, we can see that the pins are not straight across. They are a bit staggered. So when you replace one that had pins that were staggered with a potentiometer that has the pins straight across, you have to adapt and overcome. So I've taken the new one, I've trimmed off the knob, and I've bent the leads or the terminals down so that they fit in that hole, in those holes. So it won't be extremely stable, but you know, even if you look at the ones that are already on the board, they're not really stable. So I think it will be fine. So we're just going to get these down in the hole and get a lot of solder on them and let them do work. Okay. Now these two are supposed to be tied together anyway, so I'm going to go ahead and add some more solder right there in the middle, just so there's no confusion. I mean, there's not really any confusion because you can see that the mask is tied together. The trace, they're tied to the same trace, so there's no confusion, but why not? You know, why not? Good Lord, man. Probably not a good sign. God. Well, I'm not exactly happy with how this potentiometer is sitting on the board. In fact, it's not really sitting on the board. I mean, it's on the board, but it's not even. And the reason it's not even is because and you're not going to be able to see this, the terminals don't fit through the holes as well as the old potentiometers. And so if you look in the middle, you can see right there in the middle that the center terminal does not fit through the board. So that causes a teeter-totter type action from left to right on the potentiometer. But I mean, it doesn't affect the functionality, it just bothers me. We're just going to leave that and move forward with getting it working. Alright, well, we can see that the potentiometer is going to be blocking this capacitor's installation because it needs to fit right there. And you're already bumping into that capacitor. So the other option is to not use this hole here and to use just this hole and then the opposite hole and then tie the two together on the other side of the board, which is fine. So these terminals on this capacitor are larger than these holes, so you don't get a good fit. So what I'm going to do is I'm going to drill out these two holes a little bit so that I can get this capacitor sitting flush on the board, since we only have two terminals to deal with. And even though there's slight leading over on this edge, I don't think that's going to be a problem with it fitting back in the case. But I'm going to check it just in case. Basically gonna go like this. Yeah, and And see, now it clears the edge of the board. All right, the next things we're going to replace are these two transistors here, which I can't point to that, here, and the transistor that goes here are going to be replaced with a KSA 1013. And I have two that match here perfectly. There are two on the ends. I have a 201 and a 201, so I'm just going to use those since they match, and that's good enough. So let's get that going.
Now is a really good time for me to discuss why I'm actually replacing these transistors. The two transistors we're talking about replacing are Q7 and Q8. These are two PNP transistors on the ends here. And if we look at my data up at the top, you can see I have Q7 and Q8 here. If we look at the gain, they're expected to have a minimum of 70. Q7 had a gain of 67 and this one is 73. They're close, but one is a failure. And my logic about replacing the transistors on each side of these boards is that if you replace one of them, you might as well replace all of them since they're about 37 cents a piece. If we look at the data sheet for the 2SA497-0, we will see that the electrical characteristics down here at the bottom list a gain here, and there's a note that goes with it. Normally it says the gain is 40, max 240, but if you look at the note, according to the value of HFE1, it should be for 2SA497-0, which is ours, the minimum should be 70 and the maximum should be 140. So I'm thinking since we barely made 70 on one of those, Q8, and we didn't reach it on Q7, we should just replace all of those transistors. Here we are looking at the data for Q7 for the original OEM transistor. Barely gets to 70 even on one trace, and that is on the 6-volt trace, or a 6-volt line, I would say. If we look at Q8, we can see that Q8 is slightly better, and then we spend only maybe 20% below the 70% line.
Okay, so those two have been replaced. They are here. I also replaced this test point 2 lead. And then, so you have this one here, this one here. The next 4 that we need to replace are Q3, 4, 5, and 6, which are here, 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 and here. Don't remember what the original part number is, but they're going to be replaced with a KSC 2383. Okay, so here's my logic for replacing these 4, right? So you have 2 on this side, and then you have 2 on this side. So you have left and right. Okay, so they don't need to match on this side, but I would prefer they match from here to here and from here to here, just for symmetry. So what I'm going to do is I'm going to take the 218 and the 218 and put them on Q3 and Q4, I believe. And then I'm going to take the 224 and the 225 and put them on 5 and 6, whatever those correct numbers are, but it's 2, 3, 4. No, it's 3, 4, 5, and 6. Okay, so we have 6 transistors replaced. This one, and then 3, 4, 5, and 6. Down here we have Q1 goes here, and then on this side is Q2. So Q1 and Q2 originally were 2SC732s, and I'm going to replace them with onsemi KSC 1815, so KSC 1815s. And they probably don't need to be perfectly matched, but since yeah, I'm going to match them anyway. So I have a 171 here and a 171 here, so I'm just going to use those two. Okay, there is probably nothing worse than getting a transistor put in with the leads in the wrong holes. So just to cover my bases, I want to make sure that This is the base, this is the collector, and this is emitter. And I'm making an assumption there just because the ones that I've put in so far are the same. But that's not the case, or it might not be the case. So every time I put a transistor in, I'm just going to verify the pinout. So I think this is going to be the base, and this is going to be the collector, and this is going to be the emitter. But it could be completely wrong. I have no idea. So let's just check it and make sure. Here we go. Okay, yep, I got it right. Blue is the base, green is the emitter, and red is the collector. So that's correct. Center pin is the collector, base is on the right, emitter's on the left. Good. This might be a little difficult to see, but there are two electrolytic capacitors that go. One goes right here. This is electrolytic capacitor C5. Goes right in between these two transistors, which I should have already put that in first, but I didn't. And then the other one is C6, which goes right here. These are 3.3 microfarads at 35 volts, and I believe I'm going to put in 50 volt film equivalents. So I'm going to put in some WEMA caps instead of the electrolytics there. Here we go. 3.3s, 10%, 50 volts. Just for grins, let's test one of these and see how it performs. Let's use our cheap Chinese tester. Okay, so this is one of those $10, $12, $15 kind of cheap Chinese testers. You just stick the component in there, lock it down on the leads, and push the button. And it doesn't seem to work. So maybe it does, maybe it doesn't. It kind of works. 3.3 microfarads, so that's 3,305 nanofarads. 0.9 ohms of ESR. Okay, cool, that's good. So it is what it is. So there you have it. That's what we're putting in. Now we're replacing capacitors C7 and 8, which are here and here. The specifications for these two are 100 microfarads at 50 volts. I'm replacing them with 100 microfarads at 63 volts. And you can see these are the Nichicon KL series. You can actually Nichicon KL series. These, I don't think these are in the audio path, so these are not audio grade quality. All right, those two caps are in. The next two to be replaced are the ones right in front of these two. These are C11 and C12. Now these are spec'd out to be 100 microfarads at 3 volts. And I'm actually going to put in 100 microfarads at 35 volts just because that's what I have. I have some Panasonic. These are Panasonic FR series, I believe. Let's make sure. Panasonic FR. Yeah, these are the FR series. I don't know if they can see that on the screen. But they're 100 microfarads at 35 volts. And these are also not in the audio path. And I just made a mistake. Look what I did. This is the negative lead. See that? I just put that capacitor in backwards. No bueno. Now I gotta do that. Sorry, okay, glad I caught that. Let's get the polarity correct on this one. All right, well, we're getting there. It's a slow process, but it's working out. We have two more. We have 100 microfarads we've already replaced here, and 100 microfarads we've replaced here. We have one more in the front. These are 3.3 microfarads, I believe. I'm gonna have to look that up, but I'm gonna put a couple of WEMA film caps in there. So let's get that going right now. Okay, I just misspoke. These two right here are 100 microfarads. So you have 100, 100, 100, 100, 100, 100. The C1 and C2, these are 3.3 microfarads. So you have 100 on this side, 100 on this side. So I'm going to put the Nishikon UPW caps in this place right here, and we'll pull those out right now. Okay, so here are the Nishikon 100 microfarad, 20% tolerance, 63 volt UPW series, and they look like this. Let's see if I can do this with a small piece of solder. All right, let's just check our progress right now. On this board, we have two more film caps to install. We have one more large electrolytic output capacitor to install. It's a mirror of this one. And then we need to get our output transistors installed. And then I believe just two fuses, and we are ready to start testing this board. The specifications for these two capacitors, and these are the input capacitors. So this is the first thing that the audio hits when it comes into this board. So this is supposed to be a 3.3 microfarad capacitor at 10 volts. I'm putting in the same caps that I had over here for 5 and 6 as I am for 1 and 2. So these are the 3.3 microfarad at 50 volt WEMA caps. So the leads of the new cap will not fit in the holes over here that they need to go into, so I'm going to drill out that just slightly so that the capacitor will sit flush on the board. As it sits right now, it just won't go in there well enough, so we have to drill it out. Now, I've already shown you this on the other side, but you can see that the old capacitor had 4 terminals. Basically, 2 of them were tied to ground, the other one was just a support lug, and the other one was positive. Since this one only has 2, I'm going to have to do what I did on the other side, and you can see that I had to run a jumper wire for the negatives. The support hole is not used, and then this is the positive terminal. So we'll end up doing that same thing on this side. And as you can see, I drilled out these 2 holes so that I could fit the leads in there. It's kind of janky, and that's just the way it's going to have to be, because sometimes you can get parts that are perfectly a match, and sometimes you can't. And then you have to do hacks like this to make it work, and that's just the way it's going to be. Here's before the soldering, and then you'll see that after shortly. Okay, so those 2 hacks are in. We have the hack over here from the previous one, and then the better hack. I did a better job on this one than I did on the other one for sure. So those are in. All the caps, all the capacitors have been replaced. The other resistors we replaced were the emitter resistors, and those were open. So those have all been replaced. All the transistors have been replaced. Those were all bad. All the capacitors were leaking and had high ESR. So everything on this board is ready to be tested. So we've got to put the output transistors in now, and that's what we're going to do this second. All right, the way this has traditionally worked is that you have a layer of heat compound, silicone grease that goes up against your heatsink, and then you'll have a mica insulator, and then you have another layer of silicone grease on that side, and then you have your transistor. So that's traditionally the way it works, and it works well. It's just very messy. So there is an alternative to using these mica pads, and these are SIL pads, S-I-L, silicon pads, and they are cleaner because you don't use any silicone grease, and you just set them on there and put your transistor on and then tighten it down and you're done. They are not quite as efficient for heat dissipation as the mica option. Seeing as this is a lower end Pioneer receiver, I'm not going to put the SIL pads on this receiver. I'm going to use these up because I have them, and I prefer to get rid of them and use these for amplifiers that don't need as much heat dissipation. What I'm going to do is I'm going to use this thermal grease, and I'm going to use a paintbrush to put it on and to minimize the amount of this garbage that I get on my hands. But before we do that, we're going to take the new output transistors out of the package. Now the old transistors were 2SC-793s, and we are replacing those with onsemi's MJ21194 4G. That's MJ21194G, made in Mexico. Let's get these tested and then go from there.
Here are the 4 original output transistors. As you can see in the DCA Pro snippets, the gain values for Q9 through Q12 are 15, 24, 19, and 15 respectively. Here's the data sheet for these transistors, and you can see at the bottom where the green vertical and horizontal bars meet, the minimum gain should be 30 and the high should be 200. Therefore, these components are very tired. That said, the amplifier board had a short somewhere, and I assumed that it was a transistor, but it must have been somewhere else, or at least one of the 2 transistors on the right side would have had a short. It turned out to be the emitter resistor on Q11 that was the culprit. Since I want this amplifier to work perfectly for many years to come, these transistors need to be replaced anyway. I know you don't want to sit here and watch me test a bunch of output transistors. Therefore, I will simply show you a summary of the results from the DCA peak testing. The average measured gains are 72, 61, 68, and 70. 1, 2, 3, and 4 are going on the board where Q9, 10, 11, and 12 are located. The top and bottom left portions of this view are from the datasheet for the new transistors. As you can see, according to the manufacturer, the gain should range between 15 and 60. Their 10-volt sample test chart at the bottom left shows the gain versus collector current. 7 on their vertical scale means 70. I don't listen to music loudly much anymore, so I've highlighted in yellow my typical usage, which would be up to 1 amp of current draw. The graph on the bottom right is the data from the Peak Atlas tests for Q9 at the same 10 volts. This transistor is performing slightly above specifications.
Okay, so here's the strategy. The strategy is not to keep the silicone grease, the thermal grease, off of your fingers and your hands. That's only possible if you're going to wear gloves, and then you're just going to get it all over the gloves. So my strategy is to put the the thermal grease on one side of the mica insulator. Then I'll put the mica insulator on the heatsink. Then I will take a transistor and I will put the thermal grease on the transistor, and then I will sit the transistor on the other side of the non-coated mica insulator. And then after all that's done and I've gotten grease everywhere, I will clean it up. That's the strategy. I like using this little paintbrush because it's fairly consistent. It's easy to get a consistent, very thin coat of the thermal grease on the mica insulator and your fingers. So there's that. Okay. It just needs to be very thin and light. I'm just trying to be even because I'm OCD, and that's just the way it goes. So here it is, one insulator going in, and we're going to get it everywhere because that's just the way it goes. Okay, one insulator on to the heatsink. 4 insulators down, 4 transistors to go. We're going to start with this one. But as you can see, I left the dot on there. I'm going to clean that off just because I just don't want it on there. Okay, so the primary goal when applying thermal grease to the bottom of the transistors is to not get thermal grease on the leads. Yes. Come on. One last one on there. Come on. Seriously. Yeah, come on. This board is ready to test. I wouldn't say it's finished, but it's ready to test. Okay, I know this looks like a big hot mess, but I wanted to test this main amp board before I put it back in the receiver, so that if something was wrong, I wouldn't have to pull it back out. So I basically run 56 volts straight into the B+, which is right here. So this half of the board is the right channel, this half of the board is the left channel, and I'm running a 1000 hertz tone with 100 millivolts into both sides, and that is here, and it's coming over and going over to the other input. So I have output here and output here, so we can see that on the scope. Everything looks good. This is just 100 millivolts. I don't know how far I can push it, but I'm not really trying to test the board right now. I'm just trying to make sure that the board is good before I put it back in. To be fair, I did find a few other solder joints that were bad and were causing all kinds of problems. So I basically reflowed the entire board just to make sure that everything was looking good. So right now everything is running cold, ice cold, as if they weren't even on. I mean, I guess I could try and push it up a little bit and see, but I'm not trying to power test it right now. Just trying to validate that everything's working correctly, and it seems to be doing so. Okay, I've been running this for about half an hour, and the sine wave looks great on both channels. They are very closely tracking, almost they're identical basically. So it's putting out 17.6 volts into each channel, and we can see that I have an amplitude of 565 millivolts going into the input signal, or the input signal is 1 kilohertz, 565 millivolts, and I'm powering it with 56 volts like it's supposed to be at the B+, and it's been running for about a half an hour, and everything is ice cold. So that's greatness. Okay, so I figured I would just do a little THD experiment with the amp board by itself. So what I've got here is I have a 1 kilohertz tone running into the right channel with 530 millivolt input. And as you can see, I'm powering the amp with 56 volts, and the sine wave looks good on the right side. It's outputting 16.52 volts RMS, and our distortion is at 0.1466-ish. So the rated THD for this this amplifier is less than 0.5, so we're doing good there. Let's check the other channel. Okay, we're now testing the other channel, same parameters, 1 kilohertz with 530 millivolts of amplitude, and we're looking at 0.157 on the distortion, and basically this is exactly the same output. So this is great.
After putting the amplifier board back into the chassis, I wanted to run one more thermal test, and here are the results. The receiver had been playing music for a couple of hours at this point at a low listening level.
That is going to be all for video number 1. Join me in the next video where we will work on the front panel, the controls, and the power supply. In the final video, we will finish up with the tuner boards, the lights, and the external appearance. Thank you for watching.